Section 1.7, we introduced the idea of linear independence and linear dependence of a set of vectors, and the usual definition is a set of vectors v1 through vp is linearly independent if the only linear combination of those vectors that's equal to the zero vector, this is the zero vector, is the trivial one with all the coefficients 0. And linear dependence just means the opposite of independence. So if the only way you can set a linear combination of these vectors to the zero vector is by multiplying all of them by 0, which will always work, then they're said to be independent. So if they're dependent, that means there's some way without using all zeros to set a linear combination equal 0, and in that case you can take any one of these coefficients that's non-zero, there's at least one that's non-zero, and let's say it's a2, then solve for v2 in terms of the other. So if a system of vectors is dependent, that means that at least one of the vectors can be written as a linear combination of the others. And conversely, that's an equivalent definition of linear dependence, because if some vector can be written as a linear combination of the others, then you can just take them all on one side and you've got a linear combination of all the vectors equal to 0, where they're not all 0, at least the coefficient of the one on the left hand side originally is non-zero. So basically those are two different definitions. This one is more useful for actually determining if a set is dependent or independent, but the other one is a little easier to understand geometrically. So for example, let's say we're in R3, three-dimensional vectors. The vectors I, j, and k are clearly linearly independent, I being 1, 0, 0, the unit vector in the x direction, j is 0, 1, 0, k is 0, 0, 1. Those three vectors are clearly independent. Why? Because clearly no one can be written as a linear combination of the others. For example, k can't possibly be a linear combination of I and j, because I and j both have zeros in the third component. So any linear combination of I and j will still have a 0 in the third component and can't be equal to k. And similarly, j can't be a linear combination of I and k, and I can't be a linear combination of j and k. But to prove independence is usually easier to use this definition, because you don't want to go through each one and say this can't be a linear combination of the others and this one can't, and so forth. Just set a linear combination equals 0 vector, solve for the a's, and see if they have to all be 0. Another example, if you take the vectors I, j, and the vector 1, 1, 0, those are dependent because 1, 1, 0 can be written as I plus j. They're all three in the same plane, so one of them can be written as a linear combination of the others, whereas I, j, k, none of them is in the plane of the other two. So how do you actually determine if a set of vectors is independent or not in practice? For example, these three vectors here in R3, it's not obvious whether or not they're independent. You can't really tell whether v1 is a linear combination of the others and so forth. So what you do is you set a linear combination of the three vectors equal to the 0 vector, and that is equivalent to solving a linear system with those three vectors as the columns, because Vx equals 0, where V is the matrix with those three vectors as the columns. See, that's Vx is just going to be x1 times the first column of V plus x2 times the second column of V plus x3 times the third column, and you set that equal 0, and then you solve for x, reduce it down to echelon form. You end up with a row of zeros, which means the x3 is arbitrary. x1 and x2 can be in terms of x3, so you can set x3 to any non-zero number in x1 and x2, and you have a solution that's not all zeros. Therefore, those three vectors were dependent, which means that one of them must have been in the plane of the other two. On the other hand, here are three other vectors, and you do the same thing with them. Put those three in the columns of a matrix on the 0 right-hand side, the augmented matrix, reduce it down to echelon form. This time you end up with identity, which means that x3 is 0, x2 is 0, and x1 is 0, which means they were independent. What if I had given you 4 vectors in R3? You could automatically say those must be dependent. Why? Because put those in as the columns of a matrix with the right-hand side 0, reduce it down, you're bound to have at least one arbitrary variable, because even if the end up with that 1 1 1, you're going to have a fourth x4 will be arbitrary. So the number of arbitrary coefficients, remember, is n minus r, where n is the number of columns, 4 in this case, if there are 4 vectors, minus the number of non-zero rows after reduction. Well, the number of non-zero rows after reduction, if there's only 3 to begin with, the number after reduction has got to be 3 or less, so n minus r, n is 4, r is 3 or less, so it's going to be at least 1, so there'll be non-zero solutions. Therefore, 4 vectors in R3 are guaranteed to always be dependent. That makes sense geometrically. You can't have more than 3 independent vectors. If you do have 3 independent vectors, then the fourth one will be sure to be a linear combination of those 3. In fact, the next theorem generalizes this and says if you have vectors in Rm, the vectors of m components, if you have more than m vectors in Rm, it's guaranteed to be linearly dependent. The same argument, you've got p columns, so n is p, and r is m or less, so n minus r is at least 1. There's at least one arbitrary variable. So you can't have more than m independent vectors in Rm. Of course, if you have m, they might be independent or dependent, but if you have more than m, they're guaranteed to be dependent. Okay, now if A is a square matrix, this is important here. A is square. It's not it's non-singular if the columns are independent. So a square matrix with independent columns is called non-singular. If it's not square, you can't talk about singular or non-singular. We're only talking about square matrices now. But a square matrix, if the columns are independent, that means if AX equals 0, the only solution is X equals 0. The only way you can get a linear combination of the columns equal to 0 is if the coefficients of the linear combination are all 0. So square matrix, if the columns are independent, it's called non-singular. If they're dependent, it's called singular. Basically, there's good square matrices and bad square matrices. The good ones are non-singular, the columns are independent, and the only solution to AX equals 0 is 0. And furthermore, if A is non-singular, if it's a good matrix, talking about square matrices still, then AX equals B has a unique solution for any B. Why? Because if it's non-singular, that means when you reduce it down to reduced echelon form, you don't end up with a row of zeros. If you're solving AX equals B and you reduce it down, if it's non-singular, that means you're going to end up with an identity matrix, no rows of 0, and then you'll have a unique solution, AX equals 0. The only solution will be X equals 0. Well, it doesn't matter what the right-hand side is. If A reduces down to the identity, then it's going to reduce down the identity no matter what the right-hand side, so you'll have a unique solution. The unique solution will be 0 if the right-hand side is 0, and it won't be 0 if the right-hand side is not 0. So the good matrices, good square matrices, reduce down to the identity, and you'll always have a unique solution whether the right-hand side is B or 0. The bad matrices, the singular ones, where the columns are dependent, square matrices, they always reduce down and they have at least one row of zeros, which means you never have a unique solution, because you'll either have many solutions if the corresponding final elements of B corresponding to the 0 rows are 0, and if they're non-zero, you have no solution. So the good matrices, the non-singular ones, AX equals B has always a unique solution. That's why we say they're good. And the bad matrices, the singular ones, square matrices, AX equals B never has a unique solution. It always has many or no solutions. Okay, quick look at the homework. Number 14, it says there's 4 vectors. They're given over here. Are these linearly dependent or independent? Well, you don't even need to look at them because there's 4 vectors in R3 and they can't possibly be independent, so they're guaranteed to be dependent. On the other hand, these 3 vectors, they may or may not be dependent. You can't tell. You put them in as the columns and reduce down and see if you end up with a row of zeros or not. If you end up with a row of zeros, then they're dependent. Okay, problem 49 says you have a set of mutually orthogonal non-zero vectors, a set of 3 in Rm. So this could be 5-dimensional or 10-dimensional space. But if you have 3 mutually orthogonal, the dot product between any pair is 0. They're guaranteed to be linearly independent. That seems reasonable if we're talking about vectors in R3. If you have 3 mutually independent vectors, no one of them can be a linear combination of the others. But we're not talking about R3, we're talking about Rm. But it's still true, and they have a hint here telling you how to prove it, that mutually orthogonal vectors are guaranteed to be independent of each other. No one could be a linear combination of the others, and you can prove it using this hint. Problem 50 says if you have a set of dependent vectors, then adding another vector to it, it's still going to be dependent. And that's obvious if you use the second definition of dependence. So if this set is dependent, that means at least one of them is a linear combination of the others. Well, throwing in a 4th vector doesn't change the fact that one of these is a linear combination of the others, so they're still dependent. And by the way, any set of vectors that includes the 0 vector is automatically dependent because 0 can always be written as 0 times the others. So any set of vectors that has the 0 vector in it is dead. It's automatically dependent.